Alright, so we're on to 17. Here's 17a. These are optimization problems, and this one is very similar to something we did in class. We have a cylindrical can, which we're given the surface area. The surface area is 100 centimeters squared. And we're also told that the can has no top, so presumably it has sides and also has the bottom. So what does this consist of? Well, and you know, what else do we have? There's a radius of the can, r, there's a height, h, and so we know that the bottom part, which is a circle, has surface area pi r squared, and we know that the sides, which is the actual cylinder, the round part of it, anyway, is 2 pi rh. I did give that to us too. And so this means that we can conclude that pi r squared plus 2 pi rh is equal to 100. So the bottom plus the sides is equal to 100. Now we would like to maximize the volume given this surface area. And the volume is given by pi r squared h. So these are the two equations we have. There are three unknowns, and we would like to maximize v. So we need to be able to solve for one of r or h in this first equation and substitute it into this second equation so that we can express v as a function of only one variable. Now, like last time, there's really one better variable to solve for. It's h. Why? Because if I were to try to solve for r, I would be solving some sort of quadratic equation in r. That would get pretty annoying pretty quickly. So, I mean, this is even worse than what we have in class. In class, we could have just taken a square root, but here we would have literally had to solve a quadratic equation. We don't want to do that to figure out what r is in terms of h. So let's solve for h. So subtracting pi r squared from both sides, we get 2 pi rh is equal to 100 minus pi r squared. Then I'll divide both sides by 2 pi r. Both sides by 2 pi r. That tells me that h is equal to 100 minus pi r squared all over 2 pi r. Now I substitute this into the volume expression. The volume is pi r squared times h, and h is 100 minus pi r squared over 2 pi r. Now luckily some things cancel. This pi outside cancels with the pi in the denominator. The r downstairs cancels with one factor of r from outside. And so what I'm left with is r times 100 minus pi r squared over 2. So this gives me 100 r minus pi r cubed over 2. So that's my volume. And now I've got the volume just as a function of one variable. So that means that I can try to maximize it by taking the derivative, setting it equal to 0, and whatever. Although again, we should really be concerned with what is the domain of r here. R has to be bigger than 0. Excuse me. R has to be bigger than 0 because it's at least greater than or equal to 0 because it's a distance. H also has to be greater than or equal to 0, and that should give us another sort of constraint on r. Since h is greater than or equal to 0, and h is equal to 100 minus pi r squared over 2 pi r, this has to be greater than or equal to 0. So, in particular, since r is non-negative, this is greater than or equal to 0 precisely when 100 minus pi r squared is greater than or equal to 0, which happens when 100 is greater than or equal to pi r squared, which happens when 100 divided by pi is greater than or equal to r squared. And this happens, assuming that r is greater than or equal to 0, when r is less than or equal to 10 over the square root of pi, just taking the square root of this expression. So this tells us that r has to lie in the interval from 0 to 10 over root pi. This means that we can use the closed interval method. Of course, it's pretty much impossible for the radius to literally be equal to 0. That doesn't make sense, because if the radius is equal to 0, both of the surface areas are equal to 0. So really, what we were thinking about in class, at least one of our classes, is it possible for any of these quantities to actually be equal to 0? Well, here, no, it really isn't possible for the radius to be 0 at all, because then the area condition literally could not be met. However, our volume expression does allow r equal to 0 to be plugged into it. So we're not really running into any problems by allowing r to be equal to 0. In fact, it helps us out because that allows us to actually apply the closed interval method, as opposed to having to worry about using something like the first derivative test. So anyways, I keep forgetting to change the brush size here. Okay, so the volume is equal to this expression, and we're looking at the radius between 0 and 10 over root pi. We set the derivative of v equal to 0. The derivative of v is 100 minus 3 pi r squared over 2. We set this equal to 0. If this is, first of all, this is always exists, so I don't have to worry about it being not existing. So this is equal to 0 precisely when the numerator is equal to 0. The numerator is equal to 0. Great. Let's subtract 100 from both sides. We got minus 3 pi r squared is equal to minus 100. Divide both sides by 3 pi, and I get r squared is equal to 100 over 3 pi. And then I take the square root of both sides, and I know that I can take the positive square root because, again, the radius is a number which is greater than or equal to 0. So when I take the positive square root, I get r is equal to 10 over the square root of 3 pi. We should be careful to make sure that this is actually in this interval, but it is, because since 3 pi is bigger than pi, dividing by root 3 pi gives us a smaller number than dividing by root pi. So now we have to plug these numbers into the original volume expression. So we are going to plug in, make a table, and we, on the left-hand side, put in the endpoints for r. We get 0. We have 10 over the square root of 3 pi, and then we have the other endpoint, which is 10 over root pi. Now, what happens here? Let's see. So the volume, if the radius is 0, the volume has to be 0. I mean, we know what the expression for volume is. Volume is pi r squared h, so this has to be 0. Over here, when the radius is 10 over root pi, remember how we found that? That is when the height is equal to 0. If the height is equal to 0, the volume is also equal to 0. So this pretty much implies that the maximum has to occur when the radius is equal to 10 over root 3 pi. Of course, we actually care about what that value is. I've gone ahead and computed what that value is. It's 108.59, let's 58. So let's say 108.58, plugging that into the volume expression. Great. So, yeah, great. And it turns out, too, that, okay, so this is the maximum, and this happens, this is maximum volume, and this happens when the radius is equal to this. It turns out that similar to what we had going on in class, the height is also equal to this quantity when we reach this maximum volume. So, okay, great. Fantastic. That's the answer to this problem.